All right, so I want to talk a little more in greater detail about how the temperature affects reaction rates. So we kind of looked at a slide that looks like this at the beginning of this chapter. And the idea is that the activation energy for any one particular reaction is a constant. The collisions need to be sufficiently energetic to start a reaction. And at lower temperatures, you merely have smaller fractions of your sample that are going fast enough that would result in a sufficiently energetic collision. So you got two things. And so the other thing is, don't forget that average speed increases with temperature. So you're speeding them up so they are colliding more often. And when they do collide, the average energy is increased, and a greater fraction of them will have an energy above this activation threshold. But now we can get into a little more detail, be a bit more quantitative about it, and see what we can get out of that. So the temperature dependence is built into the rate constant K, which is why we always specify a particular temperature when stating a rate constant. So here's the equation that actually sums that up. And so I'm going to talk about what these points are here. So the rate constant can be equated to this thing A, called the frequency factor, or more often than not simply the pre-exponential A factor. And then it's times E raised to this ratio of negative EA over RT. So what are these? So EA is the activation energy. R is actually the gas constant that we learned about last semester, except it's expressed in different units. Instead of liter atmospheres per mole per Kelvin, it's in joules per mole per Kelvin. So you can say that today you learned that the product of pressure and volume is energy. And finally, T is the temperature, and this is very important. It must be the absolute temperature in kelvins. So let's look at this. And this, by the way, now this term right here, e to the minus whatever, EA over RT is a ratio of two energies. Remember, so let's look at the activation energy is an energy, and let's look at the denominator here. It's the product of R and T. Joules per mole per Kelvin times Kelvin. So that gives us joules per mole. So it's an energy. And this factor, E raised to this ratio, is the probability that a collision at that temperature will have an energy greater than activation energy. So this product, RT, is can be thought of as an average energy for that sample at that temperature. And this ratio will tell you what fraction of them have an energy greater than that. This term is seen a lot in chemistry and physics, E raised to the ratio of some energy in RT. And and this is how one can express a rate constant. And this is how you can build in the temperature dependence to it. So let's examine that a little bit further. So this, by the way, is the Arrhenius equation that was put forth by the Swedish chemist Svante Arrhenius, and I just like that because Svante is a fun name to say. Okay, and for this, he won the 1903 Nobel Prize in Chemistry, but not for this. All right, so this can be used to actually calculate activation energies and, by extension, the A factor. And how do you do this? Well, let's do what people have done in the olden days because it was easy and made calculations possible. We're going to turn this into a linear equation, which means taking a natural log to get rid of the exponential term. And this becomes natural log of the rate constant K equals natural log of the frequency factor A minus EA over R, and then times 1 over T. I did it this way to show you that, to map this against a linear equation. And maybe a little more explicit here. Get my pen. So this is y equals, this is going to be the intercept b plus, and this is the slope, and then 1 over t is going to be what's on the x-axis here. So you plot the natural log. So what you do is you measure or you determine the rate constant at different temperatures, plot the natural log of that rate constant versus 1 over t, and what you should get is a straight line that goes down with 1 over temperature, because the rate constant should go up with temperature. And the slope of that line, as the equation points out, should be equal to the negative EA over R. So from that, from the slope you can extract the activation energy. And if it is of interest to you from the intercept, you can determine the natural log of the frequency factor A, and then by extension, the frequency factor A. So I wanted to show you quickly what one of these determinations looks like, and it looks like this. So we've got the rate constant here measured at several temperatures. Transform it into the natural log of the rate constant, plot it versus 1 of the temperature, and you get this, in this case, remarkably linear curve. And so let's talk about the analysis here. So let's look at what the units of the slope is, because obviously Excel is dumb and has no idea about this. So the slope is always the change in y over change in x. So natural log quantities are unitless. So there's no units in the change in y, and the change in x is, so the units of x are 1 over kelvins. And so 1 over kelvins equals kelvins. So this quantity here actually has units of kelvins, and that's an important thing to be aware of. So the slope is equal to 1120 kelvins. That's equal to the quantity negative EA over R. So you can solve for the EA, and that gives us a result of about 93.1 kilojoules per mole as the activation energy for this process. So that's how we determine activation energies. Now in some cases, you might only have 2 rate temperature pairs, because sometimes it's just not feasible to measure it at a bunch of different temperatures. So in that case, the resulting equation, which is actually just basically a delta, delta x over delta y thing, reduces to this. So the natural log of rate constant at temperature 2 divided by the rate constant at temperature 1 is equal to EA over R times 1 over T1 minus 1 over T2. The other way this is often seen is to keep that negative sign in there, because there is a tendency to always do second minus first. So we can do it that way. These are mathematically equivalent. One thing I do want to point out, and I see this, and this is just a math goof, but I see it a lot. So this is that term right here is the difference of 2 fractions that have explicitly different denominators. There is a tendency to want to evaluate this by simply taking the difference of the 2 denominator terms and then inverting it or doing it, 1 divided by. Do not do this, because those are not mathematically equivalent. So no, 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 no. So what you need to do is something like this. So you need to explicitly evaluate the 2 fractions first, then take their difference. Now with most calculators, you can do that quite easily with the parentheses, like I've just drawn them, or a 1 over x key as well, but just make sure that you don't do the one that I blocked out. So explicitly evaluate the fractions, then take their difference.